folks, welcome to Chapter 1, Lesson 1, Points, Lines, and Planes. This is a point. If I arrange points as such, I get a line. The arrows at the end indicate that the line goes on forever. However, if there are no arrows in the end, we have a finite line segment. Here's a bunch of points. If they're arranged as such, they form a plane. Despite not having arrows on this plane is most likely an infinite plane that goes on forever. However, it could be a finite plane. Only context will tell us. Here's a number of ordered pairs. If I could drive a single line through them, the points are said to be collinear, meaning all on the same line. If there's a point that's not on that line, it is not collinear with the other points. Here's a number of points in space. If I'm able to drive a plane through all these points, the points are said to be coplanar. And if there's a point not on that plane, it's said to be not coplanar with the other points. Observe the room and the objects in the room. Identify line segments and finite planes in the room. Identify interesting points on the planes. Secondly, look at the walls, which are finite planes. What is the shape of the intersection of two planes? What is the shape of the intersection of three planes? Finally, look at the top of your desk, which is a finite plane, and your pen or pencil, which is a line segment. What is the shape of the intersection of a line and a plane? I'm going to come to you. And walk you around. All right. I immediately observed that there are plenty of lines in this room. The edges of my whiteboards are all lines. They're finite line segments, to be particular. Same thing with the edges of the door frame, with the edges between the wall and the ceiling. There are many lines in this room. Planes. Every one of these pictures, you could either say is a finite plane or represents an infinite plane. Likewise, you could say the same thing about this whiteboard. This whiteboard is a finite plane, or you can say it's an infinite plane representing the wall and everything that goes beyond the wall stretched out forever. Question was, identify interesting points on the planes. Well, you might say, okay, along this line right here, there's this kind of mark. That's an interesting point. But here's something more interesting. You see these pieces of paper, you'd say, oh, that's one giant plane right there, a rectangular plane. Maybe it represents an infinite plane, maybe it's a finite plane. But here's another way to look at it. This right here is just a line. And this right here is a point on that line, that piece of paper. You'd say, but I don't understand, those are planes, not points and lines. Yeah, but a point has no actual size. It's just a location. And likewise, the line is just made up of points, so it's made up of a bunch of locations. So you can see how you could interpret this to be a line, with this piece of paper being a point on that line. All right, then we're supposed to look at the walls, which are finite planes, and see the intersection of the two. Well, here's a wall, and here's another wall. Look at the intersection of the two. What shape is formed? See? It's a line. How big an intersection of three planes? Well, here's a wall, and here's the ceiling, three planes. What do you see as the intersection of the three planes? Look up there in that corner. What do you see? A point. A point. All right. All right, now is the issue of the desk. The desk is the top of the desk is a plane. It's a finite plane, it could represent an infinite plane. Now, if I took my pen, which represents a line, either a finite line or an infinite line, and I put it down on the desk, you could say, okay, the intersection is a line. The line that's on the plane has an intersection that is a line. They share that in common. But most likely, if I just took a random plane like this and a random line coming from anywhere, it would intersect the plane at a single point, and that's the most common case. All right, we have to begin to think of these 1, 2, and 3-dimensional worlds. You live in a 3-dimensional world with length, height, width. You move around in 3 dimensions. When I move through space, I'm moving in 3 dimensions. When I move just on a plane, I'm moving in 2 dimensions. When I move just on a line, and my only 2 directions that are afforded to me are forward or backward, I'm on a 1-dimensional number line. Okay, so we start here with a 1-dimensional number line. It's a real number line, so we call it R1 for real number 1. This can hold geometry in 1 dimension. So you can put a point on it. There's the point if you can't see it. And there is algebra, x equals -1. That algebra and that geometry say exactly the same thing. We've been discussing that math is a blueprint for creation. It's also a method of examining creation. But the argument is that it's an exemplar cause in the mind of God that he's always known before he created. And when he created, he had this math in his mind when he was creating. And we get to uncover his thoughts, discover his thoughts, and think his thoughts after him. How we express those thoughts, we can express them in many different languages. Just like I can say there are many things to do in English or in French, il y a beaucoup de choses à faire, I can certainly speak in geometry or algebra. So this is geometry, that point on this number line. And that right there, x equals -1, is algebra. Okay, I could also have a line segment in 1 dimensions, which is just expressed algebraically as -3 is less than x, which is less than 0. This line right here, it fills up all of R1, because all of R1 is just a line going out to infinity in both directions, and so this line does. We express that as the integral from -infinity, that way forever, all the way to +infinity, that way forever. All right, this is Cartesian coordinate plane, or R2. It's 2-dimensional space. How do you know? There are 2 number lines, 2 real number lines. That's why we call it R2. It's 2-dimensional space. You can't travel around like this, like we do in our world, but you're no longer on just a number line. You can travel along a plane, as long as you stay in the plane. This is a big upgrade. Can we put a point on a plane? Absolutely. It's this point right here. Geometrically, it's that point. Algebraically, it's 5, -2. This line, you can see it. Algebraically, it's y equals 3. You can see this line segment. Algebraically, it's y equals 3, where x is going to be limited from -3 to 3. This is a plane within the Cartesian coordinate plane. Now, it could represent an infinite plane, in which case it fills all of 2-dimensional space. Or it could just be a finite plane in which it fills that portion of the space. Okay, now this is Cartesian coordinate space R3. You'll notice there are 3 real number lines, x, y, and z. This is what we live in. This is 3 dimensions. I can move about freely through space because there I have length, width, and height. This Cartesian coordinate space is very useful, and you may or may not have encountered it before. Let's see what a point looks like. Well, here's a point. Notice you go, starting at the origin, you go over x, out y, up z. So before on a Cartesian coordinate plane, we had an ordered pair to represent that point. What do you think you're going to represent this point with on R3? An ordered triple, a number for each of the number lines, indicating a location in space. Okay, here's a line going through the origin. It used to be going up and out that way. Well, this also can be expressed algebraically as this vector value equation. The vector v equals 4 times I plus 7 times j times 3 times z, where I, j, and z are the standard basis vectors. Now, many of you have never taken physics. You may take it next year or the year after that. I just want to show you that even in 3 dimensions, we have both geometric and algebraic ways of saying the same exact thing. We can translate between these languages. All right, what is this? This is a rectangular solid of some sort. Rectangular prism, it may be called. It falls within a larger class called parallelepipeds. But this right here is a rectangular prism. Is it finite or infinite? I don't know. Context would tell me. So this may be using up all of 3-dimensional space, or it may just be that finite box. All right, so the Cartesian coordinate plane changed everything. How? Well, for thousands of years, man really mastered this field called geometry. which involves points, lines, planes, and many more shapes. And for 1,000 years, so man had mastered algebra, but putting together geometry and algebra like this was always very difficult, very hard to translate between the two. We didn't have that Rosetta Stone. The Cartesian coordinate plane is that Rosetta Stone that helps us translate between the two. Amazing. This is René Descartes. The Cartesian coordinate plane is named after him. One of the most famous mathematicians of all time. He's a great Christian, he's a great philosopher, and he's the philosopher who said, "I think, therefore I am." He's written great Christian treatises, and he's also one of the greatest mathematicians of all time. He introduced the Cartesian coordinate plane. He published it, René Descartes did, in 1637. Let's think about this. Geometry was systematized all the way back in 300 BC. So 600 BC, you have Pythagoras. He and his cult of aristocrat mathematicians are working for 300 years. Even before that, you had Thales, working for hundreds of years to put together systematized mathematics. And the only kind of math they really focused on was geometry. Right? Well, Euclid comes along in 300 BC, and he publishes the Elements, where he takes all the known geometry that have been really worked on, systematized over hundreds of years, and he puts it in a 13-volume set, which he calls the Elements. The Bible is the most published and republished book. Elements is the second to that. From the year 300 until probably the year 1600, it was the mathematical textbook that every learned mathematician used. Well, how long did it take for geometry, which was systematized at the time of Euclid in 300 BC, how long did it take before we could translate systematically between that geometry and algebra? Well, it's from 300 BC all the way to 1637 AD, so that's over 1900 years. Pretty cool. What a great, math exploded after the advent of the Cartesian coordinate system. All right, draw a Cartesian coordinate plane and on it draw the line equation, whose equation is y equals 2. Okay, I'm going to switch over here to the whiteboard. Here's a Cartesian coordinate plane, 2 dimensions, 2 real number lines. Call this x, we call this y. If this is the line 1, 2, okay? Here's y equals 2 right here. Geometry, algebra. All right, what do you see? I'll tell you, I gotta ask yourself, are you looking at 3 dimensions or 2 dimensions? Here we're looking at 3 dimensions. It's a rudimentary 3-dimensional design, but you can see it. This plane right here, which goes by the name P, is coming out at you. And then there's another line named N, which is on that plane. It's just sitting on the plane. And there's another line R, which is coming through the plane. Here, I'll show you a visual. If you're having trouble interpreting this, it's supposed to be 3 dimensions. Here's your plane. This will be the plane P. Here is the line R, and it's going right through the plane and coming out the other side. All right. So the question is, well, twofold here. One, can we name the line that is on the plane? All right, well, the name of the line is N. Do you see that? But could also be given using any 2 ordered pairs on the line. So we could say 1, N is called, can also be called, to call it N, we could call it VY. We put a little line hat on top of it. Or you call it WX. As long as I choose any 2 ordered pairs that are on the line, I can characterize the line that way. Number 2 question is, name the plane. Well, the plane is called P, you can see that. But again, we could also name it using any 3 ordered triples. So we could go with ZXY, or we could go with WYZ. As long as we have 3 points that are definitely on the plane, and yet aren't in a straight line, you can identify a plane. Think about it this way. My 2 fists, they're just hanging out in space. Can you tell me where the line is that would go between the 2? Of course, it's just the line that goes right here. But what if I had, let's say this is a 3rd fist, this eraser here, and then 2 fists like this. Can you tell now where the plane is? Yes, the plane is this sheet that's going triangularly from these 3 points. You see it? You need 3 points in space to define a definitive plane. So we can indicate things that way. All right, this may be hard to read from your vantage point. Algebra, lines A and B and C and D intersect at E for A, -2, 4, B, 0, -2, C, -3, 0, and D, 3, 3 on a coordinate plane. Point F is coplanar with these points, but not collinear with A, B, or C, D. We're supposed to graph each of the points in the lines A, B, and C, D. Well, first we have to ask ourselves, is this 1-dimensional, 2-dimensional, or 3-dimensional? Am I in R1, R2, or R3? The answer is you're in R2. How do you know? Context, look over here. This ordered pair is given. It's not an ordered triple, it's an ordered pair. Okay, I must be in a Cartesian coordinate plane situation. So I draw my 2-dimensional Cartesian coordinate plane. Put some tick marks. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. Like that. XY plane, most likely what we're going to call it. A is at -2, 4. That's A. B is at 0, -2. C is at -3, 0. And D is at 3, 3. All right, and we're asked to graph the line AB. Well, AB is the line that goes through these 2 ordered pairs. We're asked to graph the line CD. Well, that's the line that goes through these 2 ordered pairs. And we're told that F is coplanar with all of these points, but not collinear with AB or CD. So could we choose F to be over here? No, because then it would be collinear with AB. Can we choose F to go here? No, it would be collinear with CD. Can we choose F to be right here? No, because it would be collinear with AB. But we could choose F to, say, be over here. There's an infinite number of choices, but that's one choice. F is clearly coplanar with A, D, C, and B. They're all on this plane, right? This infinite plane here. It's Cartesian coordinate plane, but not collinear with CD or AB. All right, this next idea, it says QR, or on B now, QR intersects plane T at point S. So what are we in? It says draw the surface to represent the plane T and label it. Draw a dot for S anywhere in the plane and a dot that is not on plane T for point Q, and draw a line through Q and S. And what am I in? Am I in 2 dimensions or 3 dimensions? Well, 3 dimensions. So how can we draw that easily? We could draw this representation of a plane. Again, this is the plane coming out at you. And we say that the name of this plane is T. Then we are supposed to put a point S anywhere on that plane, so we'll call this the point S. And we're also supposed to have a point Q that's not on the plane. All right. And we draw a line through QS. All right, notice you can now see what's going on. I'll show you again. Here's a plane, here's a line going through the plane, and that's being shown here. So this is, you're in R3 here, 3-dimensional space. All right, good. Then draw another dot that's on the line and label it R. Okay, I can put that anywhere, I'll just put it up here. That's it. Let's keep going. How many planes appear in this figure? Well, this figure is in your book. It's called example 4 if you're having trouble seeing it from a distance. Well, it looks like you have a 5-sided polygon here. pentagon. So there must be 5 planes coming up. They look like finite planes, but they might keep going, in which case they'd be infinite planes. It's just not shown. And then there's this 6th plane right here, which either be finite or infinite. So there's 6 planes, is what we would say. Name 3 points that are collinear. Well, it's hard to identify 3 collinear points here, right? Because if you have HG, you don't know what the next point is. If you have LM, you know what the next point is. They're not named. Oh, but over here they are, DKJ, along that line. Name the intersection of plane HDG with X. HDG is this plane that's right out here, and X is the name of this plane. So when this plane that's coming down is meeting this plane, we're meeting on this line, and this line has the order pairs HG. So we call it line HG. At what point do LM and EF intersect? Okay, LM is this line going up and down. EF is this line that's on the plane X, the one coming out at you, and then it's going this way. The answer is they're never really going to intersect. They're going to miss each other. All right, are points ED, F, and G coplanar? E, D, F, and G, are they coplanar? No. EDF is on a plane, DFG is on a plane, but you have 2 planes that are like this, so they're not coplanar. Coplanar, all the points have to be on the same plane. At what point or what line do planes JDH, that's JDH, JDE, JDE, EDF, EDF intersect? Well, we have 3 planes, 1, 2, 3, all coming up to meet at one point. It's like that corner we saw. We had the ceiling, the wall, and the wall coming together, came together at a point. That happens most of the time when you have 3 random planes. All right. Use the figure to name each of the following. A line containing point X. There's only one line containing point X. We can call it M, because it's named down here. We can call it by the order of pairs Y and R. And just make sure you put the symbol for a line above it. Number 2, a line containing the point Z. Here's the only line containing the point Z is going up and down, and that's the line L. You could also call it RZ, based on the 2 ordered pairs. A plane containing W and R. Well, that's this plane, the plane's coming at you. We call it plane B. We could also call it by any 3 ordered pairs that are on the plane. So R, W, Y. All right. Name a geometric term modeled by each object. A tightrope. Let's see, a tightrope. Pull it tight, it becomes like a line segment. A floor. If you stand on a floor and it's level, it's going to be a plane. Draw and label a figure for each relationship. A line with a coordinate plane contains 0, -5. All right, so going over 0 and down -5, that's A. And then B is 3, 1. So go over 3, up 1. Maybe that's like right around here. And a point C that is not collinear with AB. Well, any point that's collinear with AB is going to be on the line. So if I just choose a point out here, that is definitely not collinear with AB. Okay, that's number 6. Number 7. Plane Z contains at least X, Y, and W. Lines X and Y intersect at point V, and lines X and W intersect at point P. So we need a plane Z, so let's draw that. Notice I'm always drawing these parallelograms, as they seem in our minds to indicate a plane. You can use a triangle or a circle, it doesn't matter. If it's a finite plane or an infinite plane, you can use it. As long as it's flat. Plane Z says contains lines X, Y, and Z. So maybe this is line X, this is line Y, and maybe this is line Z. Lines X and Y are going to intersect at point V. All right, let's see. So they're going to intersect at point V. So we actually want to show that intersection. So let's have this be X and Y, and therefore they'll intersect right here at point B. And lines X and W, that's X. Oh, sorry, the lines weren't X, Y, and Z, they're X, Y, and W. So let's put W up there. Lines X and W intersect at P. All right, so maybe we go like this. There, X and W are intersecting at point P. This is W. All right, there's many configurations you could have come up with here. How many planes are shown in the figure? Okay, well, you have a triangular prism. That's what that's called. It's the three-dimensional shape. There's a plane, plane, and a plane. It's a triangle. And then there's the two triangular faces. So that's a total of, for number 8, 5 planes. Number 9 says, name 3 points that are collinear. Well, so the A, C, and E are all on that triangular face. That'll work. These 3 points are collinear. A, C, and E. Number 10 says, are points A, H, J, and D coplanar? A, H, J, and D, are they coplanar? Well, no. A, H, and D could be on that far side of a plane, but J certainly wouldn't be. So the answer is no. Number 11 are points B, D, and F coplanar. B, D, and F, yes, they're on that far triangle, so they're coplanar. Number 12 says, astronomy. Ursa Minor, or the Little Dipper, is a constellation made up of 7 stars in the northern sky, including the star Polaris. The diagram at the right shows the arrangements of the stars in the constellation. What geometric figures are modeled by the stars? Okay, this is supposed to be a 2-dimensional figure. In reality, the stars are at all different positions in 3-dimensional space, but we're kind of collapsing it down to just a 2-dimensional picture, and that's all we're dealing with here, dealing with this plane, okay? What geometric figures are modeled by the stars? These are clearly points. Part B, are stars 1, 2, and 3 collinear? Here's 1, here's 2, and here's 3. No. 1 and 2 are on the same line, 2 and 3 on the same line, but 1, 2, and 3 are not on the same line, not collinear. And then C, are Polaris, star 2, and star 6 coplanar on the map? That's Polaris, star 2, star 6. Yes, they're all on this 2-dimensional plane. Okay, you have homework. You'll on average have 20 problems of homework. Your homework is problems 13 through 39 odd, which means you'll count by 2s, 13, 15, 17, 19. And then you're gonna have problems 41 through 61, every other odd. What does that mean? It means you count by 4s, right? So it'll be 41, 45, 49, and so on and so forth. If you put it together, you have 20 problems for homework. Guys, I hope you're into this lesson. If you have any questions, you are always welcome to come during lunch. I eat during lunch, but I'm also available to you during lunch, so you can just come visit me in my classroom. You can also come after school. I'll just open the doors, make sure there's someone else around, and you can certainly get help after school as well. That's what I'm here for. Your success, your growth, your thinking God's thoughts after Him, your appreciating the beauty and orderliness of God's creation as understood through the language of math. And hopefully enrich you and also make you very skillful in this endeavor so you can learn more in the future. All right, thanks folks.